Smart contracts are the building blocks for the future of the internet. But if you want to become a highly sought after blockchain developer, then you need to master the right smart contract developer frameworks that will help you get the job done fast. We've seen tons of different blockchain frameworks pop up in the past, like Truffle and Hardhat. But in today's video, I want to introduce you to a blockchain development framework that I see lots of professional developers using. And you definitely want to put this on your radar if you want to become a blockchain master yourself. I'm going to reveal exactly what it is in this video today and how you can get started using it right now. I'm going to show you everything you need to know as a blockchain developer myself who works with this technology on a daily basis. So if you're new around here, hey, I'm Gregory, and on this channel, I turn you into a blockchain master. So if that's something that you're interested in, then smash that like button down below for the YouTube algorithm and subscribe to this channel. And if you want to become a blockchain master step-by-step from start to finish, then I can show you how to do that over at dappuniversity.com/bootcamp. All right, so let's get into this. Let's talk about this smart contract development framework that I see getting used by lots of professional developers lately. Well, it's called Foundry. And today's video, I want to show you why it's so valuable and how you can get started using it today. So I've invited my assistant Victor onto the channel today to present on this topic. He's going to show you everything that you need to know to get up to speed with Foundry in no time. And if you like what you see in today's video, this is a free preview of all the amazing content that we put out every single week inside of Blockchain Mastery University. And so I'll include more details at the end of this video on how you can get into that. So that being said, let's jump in and get started.
Today we're going to talk about Foundry and how to use it. Foundry is a great blockchain and smart contract development framework that a lot of blockchain developers use, and it's a newer framework. And we already did a tutorial on this Foundry framework, but now I have more experience, I've used it a lot, and I have a lot to share. So even if you're a beginner developer, or even if you have used other frameworks like Truffle or Hardhat, this tutorial can be very useful for you. Because you can use Foundry for other things that where the other smart contract development frameworks lack. For example, you can use Foundry just to interact with smart contracts that you deployed on Etherscan. You can also use Foundry to deploy, develop, test, and compile and debug smart contracts. So it's this very versatile framework that we'll learn in this tutorial. So if that sounds good, let's get started. So in this video, we'll start off by just installing Foundry. We will start off with some theory on what is Foundry, how to use it. We'll create a Foundry project. I've already created one. Once we install Foundry, we'll learn the common Foundry commands, like how to interact with contracts, how to compile them, deploy them, how to run tests, etc. Then I'll give you some template code snippets. These are some Solidity code snippets that we oftentimes use, like how to transfer Ether, how to call and interact with a smart contract function. I've already said we'll develop contracts, we'll deploy them on a testnet, we'll write tests against them, then we'll learn how to fork the mainnet and run tests on the forked mainnet. We'll learn how to verify a contract while we deploy it. We'll learn how to interact with a contract that is already deployed from the terminal just by using one command. And we'll learn a lot more. This is not all that we're going to learn. So I'm not going to hold back. I'm going to talk about everything I've learned the past few months just using Foundry. So with that out of the way, let's get started and jump into VS Code. So first things first, when you download this project, you have a file structure that looks like this. And you may not have the GitHub and cache files, but you definitely have the library folder. Then we have an out folder. This is all, again, you're probably not going to have this. This only it's created when you compile the contracts. Library is a folder where we store all of our libraries for this project. We have a scripts folder. I think we have this in Hardhat. This is where we'll write all the scripts for our project. Then we have a source folder. This source folder is where we'll write the contracts. This same folder was called contracts in Hardhat. We have a test folder. This test folder is where we'll write the tests. We have a .env file. Again, this is not mandatory. This is where you store all the environment variables. We have a git ignore file. This is just a file that tells Git what files to ignore and not push to GitHub. We have a git modules files. This is where we'll tell Foundry on what git modules we want to install. Then we have a Foundry toml file. This is like hardhat config file where you can configure stuff. Then we have a make file, and you'll see why we need this. But this file basically helps you. It's like a package.json file in hardhat. It allows you to define commands and run different scripts. And finally, we have the readme folder or file where we'll just write the documentation for this project itself. So first things first, let's start with the source folder and with this number contract. So this is how you would import a library, very similarly like we would in Hardhat. Just do import open Zeppelin contracts access and you have the ownable contract. Let's start off with how you will install these libraries. So this is why we have the make file for. So inside here you have a install command defined, and once you install Foundry, which we can do by just running this command that is specified in the Foundry tutorial here, and then just run Foundry up. Now you have access. Once you've done those commands and installed Foundry, you have access to Forge help and the cast command and anvil command. And these different commands are for different purposes. Forge, we use that to develop, deploy, compile contracts. Cast we use to maybe convert some decimal number into hexadecimals, to also interact with contracts. And anvil we usually use to fork the mainnet and those types of stuff. So once you install Foundry, we can initialize a project by doing forge init and the name of our project. And this is how this project was created. Now to install dependencies, Foundry is different in terms of how it installs dependencies. Instead of using the hardhat way with package.json and installing node modules, it's way simpler in Foundry. Everything we install is basically a GitHub repository, and since it is, Forge or Foundry uses GitHub modules, and you can install those if you just type in Forge install, and you have access to Forge once you install Foundry, then the name of the owner of the repository, and then the actual repository that you want to install on GitHub. So OpenZeppelin is the organization name, the owner name of this repository, and this is the repository name we want to install. And this is how you can install dependencies one by one. But I have a way to install these using the make file, where you just define a command which you can run by just doing make and then install. In this case, we have also command for deploy, etc, but we're only going to use this one. When we run this command, all these commands will run. So we'll not only install OpenZeppelin, but also install Soulmate, ForgeSTD, and DSTest. And you can run this command by just saying make install. So once you've created your contract, you can develop, or your project, you can develop contract in the source directory. So I've developed here one contract named a number, which inherits from ownable. Then I have a number, which is 10, and then I have a string name that can be changed with this return number 10 function. This will both return number 10 and will modify the name state variable. And you'll see why we need this later. So this takes in string name as an argument and changes the name in this contract. This is an external payable function, so it means it can receive Ether. Then we have set number, and we have increment function. In the increment function, we'll just increment the number state variable. This can be only called by the owner, and you'll see why we need this later when we write the test for this number contract. This is payable function. Again, it can and it should receive Ether. It should receive 1 Ether, and once it receives, it will change the number to this new number. So that's all I had to share about the number contract. Let's jump into the second contract we have, which is the template contract. And in this one, I have the code snippets I was talking about. So we have some template code snippets that you'll oftentimes use in Foundry. So this contract template, let's start here. It has a variable named C, which is 1. It has a bytes output variable and a number contract. We have an interface to the iNumber contract because we want to use its set number function. So in the constructor, we just pass in the number address. Then we create an instance of the number contract because we need this to interact with the number contract. We have these state variables. We'll run invariant tests and we'll see what is invariant test. That's why we need the should always be 0 variable and the hidden value. And we'll also run fuzz tests. So we'll learn what are invariant tests and what are fuzz tests and write these tests practically. So next I have a code snippet that will help you to just calculate how much gas we have left and the gas usage of certain action code snippet in Solidity. So we have a optimized function and a not optimized function. And the point here is that using C++ will use more gas than using ++C. And C was a state variable here. So optimized, it returns a uint variable gas used, and gas used is just defined here, so we don't have to declare it anywhere else. We can just say gas used equal to this. We can just very simply calculate the gas usage by saying the start gas will be this gas left function. So when you call the function, it uses some gas even before it comes to here, but we want to start from here and end here. So we can only encapsulate this line of code. And the gas used will be the start gas minus the gas left. So very simply, we just calculate how much gas we have. Then we are importing the console log or the console sol contract from the ForgeSTD library. And the ForgeSTD library is a very well-known library in Foundry that just helps you overall in your workflow as a blockchain developer. And there are many ways to print out and log something in Foundry. And one way is to just import this console.sol contract. And we can see we can print out whenever now we run this not optimized function, it will print out working in contract. And you can do this by saying just console log and put your string here. Then from the template contract, we have a set number and send it function. Here we're just practicing how we can call a function, how we can both call a function from a contract and send ether in that function if it's payable, which it is. So here, this is the syntax. You pass in the value and the message that value, which is how much ether we are sending in this function. And we are just calling the function and passing in the number because we want to set this number to something. Then we have a call function, and this is the same thing I want to demonstrate here. This is another way you can interact with smart contracts, but instead of calling the function directly, we'll use the low-level call method. This function takes in a name. This name is passed in here when we call this function, because we want to call the return number 10, which takes in a name as an argument. This is also a payable function because we'll send ether. We want this function to be payable, so we can send ether inside this function and this function will transfer the ether we sent to it to the return number 10 function. Let's see how we call this return number 10. So all we need to do is have the address of the number contract, which we already have an instance of the number contract. So we'll just say, hey, we want the address of this instance. Then we'll say .call. This will call the call function on this address. And then we can specify in curly brackets the value we want to pass in. The value is, again, the ether we want to pass in. Here is the message.value, so here is, it's not a hard-coded one, it's just how much you pass in. And here we have 200, and 200 means 200 weight, not 200 ether. And then we're specifying the gas. This is also what you can do in a call function. You can pass in the gas you want. It can be hard-coded. Once this call is done, we require that this is a successful or the call failed. So this call returns two variables, which is the data returned that you can check out in the bytes output state variable, and then the success, which is indicating whether the call was successful or not. Next thing I want to show you is the tests I've wrote that you can do as well for the number and template contract. So if you go into the test directory and into the number.test, you can see that you need to name these files. So the name of the test, and say .t for test.so. So it's a bit different from writing contracts. And you can see the tests in Foundry are written in Solidity. So this is a bit different from Hardhat, where we write tests in JavaScript. But this allows us to not have this context switching between languages. So one time you write Solidity, then you need to context switch to JavaScript. But this makes the job of writing tests easier. So let's see, how do we really write tests in Foundry? First, we want to import our contract that we are writing tests against. Then we'll import the test.so contract from the Forge std library, and we'll say contract. So our test is basically a contract. We'll name this number test, and this number test will inherit from the test contract we inherited here. And this test contract is just a contract that will provide all the functionality we need to write tests. Then we have an instance of our contract that we want to test against for obvious reasons. We have a setup function that is like before each, which will just deploy our number contract. We have an each test now. This is similar to an if block in Hardhat. Each test will be a function in Solidity. As you can see, this setup function was similar to the before each function in Hardhat, for any one of you that is using Hardhat. And these tests are the it blocks similar to in a Hardhat way. So we have each test as a function, and that need to be prefixed with the test word, and then just whatever you are testing. Usually that's the common way of writing tests. So here in the test initial number tests, we are expected to have 10 because that's, we go into our contract, we expect to have 10 as the value in our number variable, because that's what we have as our initial value. So the expected is 10. The actual is the number contract instance dot number, and each variable that is public, state variable that is public, has a getter function that you can call, which we are doing right here. Then we have this assert equal functions that we get from Foundry, where we can check a value against the expected value and return an error message if this is not the case. So we have a similar thing with Hardhat. Here we are testing the set number function, and we'll learn here about cheat codes in Foundry. So cheat codes are this a way of manipulating the blockchain and the message.sender so you can more easily simulate a real world scenario. And that's what we are using here. We are saying vm.deal address does this 1 ether. So here with the deal, we're saying this address will have 1 ether. This is a cheat code we're using. Then we have expected value is 20. And it is 20 because we're calling the setNumber function on this number contract. And we're passing in the 1 ether that we have here. We're setting it to 20. Then we'll get the actual number that is set after we call the setNumber function, and we'll again do assert equal. Lastly, we have a test increment function that will assert first of all if the owner is this address. Then we'll expect that the value is 11. Once we increment it, we'll get the actual and assert equal that the number should be incremented by 1. Then we have the template test, which is a bit longer, but we'll learn a lot of stuff here. First of which we have we're importing the tests, we're importing console log. You can use this console log both in contracts and in tests. We're importing the template contract, similarly like we did in the previous tests. We're importing this std invariant and the IERC20 interface. So this test will inherit again from the test contract, template contract from the Forge std library. And we want to have both the template and the number contract instances. And we want to have an instance of the USDC contract. And this is of type IERC20. So this is just an ERC20 contract. And we'll need this later when we want to transfer money to a contract. Of course, on the forked mainnet, which is just a copy of the mainnet. It's not the real thing, and we're not transferring real funds. We have a setup function where we have the number contract and the template contract where we are just initializing those. Of course, we're passing in the address of the number contract in the template contract. Then we have test optimized. Here we just emit the gas usage of the optimized function, and this is another way you can emit and print out logout stuff in Foundry just by using these events that are defined in our test. And here we are just testing the optimized function we wrote in the template contract, if you remember. And in the same way, we're testing the not optimized function. And we'll see the console log once we run the test. Then we have the test set number and send it function, where we say Alice is this address, which is my address. Then I want to send 1 ether to Alice. And we'll run this test on the local network, so on the local host. Then we want to say, hey, Alice is going to make all these transactions, or the next transaction only, with the prank cheat code. And we use deal to send 1 ether to Alice, but we use prank to make Alice the message.sender. And we'll call the set number and send it function, and we'll transfer 1 ether, and we'll set the number to 15. Then we expect this number that we get from this function to be 15, and the number contract to have a balance of 1 ether. Then we have increment with other account function. So here we will use the expect revert cheat code from Foundry to expect that this function will fail. And first we type the cheat code, and then we do the transaction, which is doing increment by an account that is not the owner. And we use another cheat code here, which is the start prank and stop prank. In between those two, start prank and the stop prank cheat code, we can put any transactions here. And the message sender will be the address .0, as we say here. So this is different from the prank because we can post multiple transactions, but with prank only refers to the next transaction. Finally, we have the test call function, which will just say, hey, the address does this. We want to have a 300 way because we'll send 200 to when we call this call function. We'll pass in a name, then we'll just assert equal that the name is equal to the name we passed in. And you can see we're just calling the function, passing in the guess and the name. And finally, we'll just assert equal. Then we have a interesting test where we'll run this test while we fork the mainnet. And we'll prank that we are this person, this well that has USDC, and then we'll transfer to this address that doesn't have any USDC, and you can check this on Etherscan. Then we'll check and we'll print out the balance of this person, and we'll assert equal that this address that we sent USDC to has this amount that we sent. Finally, we have an invariant and a fuzz test. And let's define fuzz tests. So fuzz tests are these tests where fuzzing basically is a concept where you pass in any random data in the test in order to make the test fail. So this is how we test it. We just pass in random data, which is of type uint 256. And this random data ranges from 0 to everything a uint 256 can hold. And the goal is we'll do a lot of runs. So we'll try again and again, multiple runs, multiple iterations. We'll run this test not only once, but multiple times. And you can specify the runs in the Foundry TML file. We'll see that in a second. And here we just say, hey, template contract that is always 0, pass in the random data. And the is always zeros is a function that we defined here. So we pass that takes in a data, which is uint. We have an if statement, which is commented out for this function to pass. So if the data is 2, should always be 0 is equal to 1, or if the hidden value is equal to 7, it should always equal to 0 be 1. So for both the fuzz test and the invariant test to pass, these need to be commented out. So the invariant test or the fuzz test, the fuzz test is like stateless fuzzing. So it will, on every new iteration, on every new run, it will have the same, the data will be reset. Invariant test is different. It will be stateful, and that's why we need to comment out this. And as you can see, for the invariant test, we are just putting invariant here instead of test. And with the invariant test, invariant is basically a condition that needs to, some truth that needs to hold true throughout the life cycle of the contract. So that means that in our case, we want this function or this variable to always be 0. And we're just checking that. And the invariant test will try to break this invariant. And if it does, that means we have a bug in our code. And that's how we test for these contracts. And lastly, to end this tutorial, I'm going to show you all the commands you can use to run tests, verify, interact with a contract that is already deployed, verify a contract while you deploy it, or verify it if it's already pre-deployed. So we already know this command, what it is used for. Then we have forge tests, which runs all the tests. If you want to run a specific test, then you can do that with running forge tests -- match path and provide the path of your test. This is to run a specific test file. If you want to increase the verbosity, you can pass in -vv. This will also not only run the test, but it will run all the console logs, and you can check the verbosity types later down this readme file. To run a specific test, you can do forge test -m and the name of our test. This is a single function that you can run. To skip a specific test, and we'll need this whenever we run this template test file, because this test forking and sending ether test it can only be run when you fork the mainnet. So we want to skip this whenever we're running this test on the local host. And you can do this by saying no match test and the name of our test function. Then we have all the assert equal things that you can assert equal, you can assert true, and you can find all of the others here. Then we have logging. Logging has different verbosity. You can either do 2Vs, which is logs emitted during tests. These are stack traces are also displayed. You can increase this up to 5V. To fork the mainnet or to run the local development blockchain, you just do anvil command. To see any other flags you can add to this command, just do anvil help. To deploy a contract, you just do forge create the RPC URL of the blockchain you want to deploy it to, the private key, and then specify the path and not only the path but also the name of the contract, and maybe passing a constructor argument. Then we have the cast command, and this is used to interact with contract that is deployed on the local development blockchain, or I've used it to interact with contracts deployed on a testnet. So what you can do to call any function on a deployed smart contract is just call the RPC URL of the blockchain that the contract is deployed to. This can be Goerli or any other. Then the contract address of the contract you want to interact with, the function, the type, the arguments that it accepts, and then the private key actual value. And of course, after you do this, you need to pass in the value of this argument. To fork the mainnet, you just do anvil fork URL and the URL of the mainnet or any other blockchain you want to fork. We have the cheat codes that can be found here on this link. To impersonate account, which we have already done by using the prank cheat code. To use the debugger, you have to specify --debug. And to verify a contract, you just add --verify upon deployment. Now to show you how I've run tests. So I want to run the template test file. I'll say forge test --v match path and run this file. You can see all the tests pass. I've run it with second verbosity 2Vs, and this one test fails because this is a fork. For us to skip this test, we need to do forge test match the path, and they say no match test, and provide the test we don't want to run, we want to skip. And you can see now all the tests pass.
All right, so that's an overview of Foundry and how you can get started as a developer. And so if you like what you see in this video today and you want to become a blockchain master, then as always, smash that like button down below for the YouTube algorithm to subscribe to this channel. But you can unlock more videos just like this every single week, and I can personally show you how to become a blockchain master step by step to finish over at dappuniversity.com/bootcamp. You really don't have to be an expert to get started today. I've helped people with zero coding experience become real world blockchain developers in a matter of months. So that's all I've got. Until next time, thanks for watching Dapp University.